Welcome everyone. Thank you for taking the time to join us for this webinar session. My name is Dennis, and I will moderate today's webinar with the subject, the importance of reliability when plating electrolytic stack blind microwires. First and foremost, I would like to introduce to you Roland Herold, who is our speaker and subject expert. Roland joined the company back in 1987, initially as materials science specialist. Later, in numerous positions in wet chemical metallization technologies for electronics application, until he was appointed in his current role as a senior specialist electroplating for our electrolytic plating technology division. He is a true expert in his field, and we are excited to have him here with us today. A couple of words about the webinar. The webinar will be divided into two parts, 40 minutes presentation and 15 minutes Q&A session. I encourage you to raise questions from the beginning of Roland's presentation and therefore to use the Q&A function, which you can find on the top right corner of your screen. Your questions will be visible only to me and Roland, therefore do not hesitate to ask any related to the topic question. We'll try to cover as many questions as possible during the planned Q&A session at the end of the presentation. If the time allows, we will answer all questions right away. Also, Roland will be available after the webinar to reach out to you via email. Last but not least, if you face any technical issues, please make sure to enter the webinar via the latest versions of Chrome or Firefox browsers. Now let me hand over to Roland. Please enjoy the session.
Thank you, Dennis. Hello, and welcome to our webinar about the stacked microwire reliability in regard of electroplated copper. Since several years, Atotech now cooperates with PCB OEMs and EMS to improve the interface bond reliability of stacked microwires, especially for increased thermo-mechanical requirements. This is very important nowadays to understand better what are the interaction of the processes on the microwire interfaces. Today, I'm very happy to present some of our findings in the regard of electroplating copper. And therefore, I will briefly introduce you into the problem itself. And we will also take a closer look at the multiple possibilities from where the problems comes from when it's about the interface integrity of microwires, followed by the possibilities, how can I determine this integrity quality of the microwire interfaces? And then we will make a deeper dive into electroplating of copper. And here we will look what the additives are doing, what is their function, and how get they adsorbed on surfaces. And we will also discuss how to control this adsorption of additives, especially, of course, on such microwire interfaces. At the end, allow me also to present some of our latest electroplating developments in this regard for vertical application and also for horizontal application. So now let's start with the problem itself. So nowadays, build-ups of stacked microwires are very common in several printed circuit board applications. But by increased requirements for the thermal mechanical stability of these build-ups, the industry focus now on very strong test methods, for example, reflow simulations. And here it was found that the interface reliability is quite often disturbed by any pollution, by any kind of contamination, or it is disturbed by microvoiding. These are the two main reasons found to be responsible that the microwire integrity is not good enough, that the thermomechanical stress can lead to separations and finally to a failing of the build-up in the field. And because the reasons can be so many, you see here not exhaustive, complete fishbone diagram, but you see at least some of the main reasons um, or the main process fields which have a direct impact to the quality of the target pad of microwires. Apart from the materials and the build-up parameter itself and the drilling of the features in such build-ups, of course, the wet chemical processing of the build-ups is of major importance to avoid any interface contamination or interface weakness of the build of the stacked microwires. And as I mentioned already, we will, during this webinar, focus on the electroplating kappa process. For sure, all of you are aware that a good pre-treatment, a good cleaning of the microwires is essential, that later the metallization you apply to these microwires have a good bond to the interface. However, apart from this cleaning and preparation of the features, of the drill holes, of the microwires, it is really important also how you run the wet chemical processes. And here we have, of course, on one hand, usually the electroless metallization to make the holes conductive. And this will be followed by electroplating of kappa, finally to fill up the microwires with kappa. And here, Atotech study the mechanisms of additive adsorption and interface cleanliness very much in the past years, not only for printed circuit board application, also for the semiconductor industry. This is of major interest to have a clear control over the adsorption of additives, and therefore we must check all the influencing parameter which are contributing to such kind of additive adsorption to keep it as low as possible, of course. And therefore, we need to discuss a bit more in detail this electroplating application. But before we go into the parameters and in the discussion of electroplating additives, allow me to give you a short an overview about the possible test methods, because you can do a lot of testing of your build-ups, and maybe you never get a clear response of this testing procedure, if your build-up is now really safe and reliable, or if it's not safe and reliable. For sure, in testing, you always exceed the normal requirements of your build-ups to find out where is the limit, where do I have at the end the point of failing of my build-up. And you see here a normal, you see an overview of the standard test procedures, which are well known and specified by IPC. And especially one method is common nowadays, more in the focus, and you can see it highlighted here by a rectangular red dotted box. This is the reflow simulation. This method is nowadays the most important and most helpful stress testing method to find out if your build-up is really reliable, if the interface integrity is good enough to survive thermal stress situations. What is important in testing the interface integrity, that you determine the interface connection during you apply the thermal mechanical stress to your build-up. That means you have to measure the resistance of your build-up during you apply this thermal stress, because during the thermal stress, the expansion of the printed circuit board is very high, and only in this condition you will have then the highest resistance, which you need to determine that you know, okay, from its prediction, you can then assume when your build-up will be failing. So famous online testing methods are thermal cycle methods, interconnect stress testing, but you see also here again in a red box highlighted the OM thermal stress tester. It is during a reflow simulation determining the resistance increase of interfaces between stacked microwires. And here you get then a very clear feedback and a very clear result in regard of the reliability. This method is very important, as I said, nowadays, to judge if your process optimization really was at the end in improving the quality of the buildup. So now let's continue with the electroplating process itself. Here you will have an overview about the typical plating additives which are used in the industry for copper filling microwires. Starting with chloride ions, these are very important in copper plating processes as a complexing agent for the other organic additives we are using in electroplating of copper. Chloride ions are in a very low concentration in the solution, but very important for complexing the organic additives. We have then a brightener in the solution. This brightener is also called accelerator, and it is usually a kind of a sulfur-containing molecule. We have a leveler containing nitrogen as a part of the amine groups in leveler, and we have a carrier, which is usually a non-ionic polymer. This overview should give you an idea now what elements you have to expect on the interface of stacked microwires when the nucleation of the electroplating copper process starts. So this overview is to give you a better understanding when you analyze the purity and the cleanliness of interfaces between stacked microwires, which elements give you feedback about the type of contamination. Of course, carbon and oxygen are elements you find in any kind of wet chemical organic solutions. And it might be that cleaning solutions or other processes remain some of their chemicals on the interface. But when you find chloride, sulfur, or nitrogen, then it's already much more likely that these are impurities caused by the electroplating copper process. And here you see now an example how to analyze the co-deposition and adsorption of organic additives at interfaces. Here you see a stacked wire built up, and you see in an area where the integrity is disturbed. You see here an analysis done by our Berlin department, and you can see by scanning transmission electron microscopy, you see we can identify the location of different elements. For example, you see here palladium and nickel. These are elements usually from the electrolytic copper deposition. We can identify exactly where they are, so we know exactly where the electrolytic copper layer is. But we also can identify with this STEM method, we can identify chloride, sulfur, oxygen and carbon. Nitrogen was here not visible, so it's not shown as an indication. But with this scanning transmission electron microscope, you have already a chance to find out, okay, do I have typical elements from electroplated copper processes in the interface? Or are these interfaces free from these elements? So you know better what process you have later to troubleshoot, if you know what elements are typical for a process. Another very common method nowadays to identify elements of interest Inside metal deposits and also at the interface of a metal deposit is the so-called DSIMS analysis, dynamic secondary ion mass spectroscopy. Here you have an example of electrolytic nickel and electrolytic copper plated, and you see we analyze the concentration of the elements of interest like carbon, oxygen, sulfur, chloride, chlorine, and nitrogen. And you see in the nickel deposit, we have a higher concentration of these elements in general in this nickel bulk deposit. And you see the interface is much higher um, contaminated with these elements. So you see here at the interface between electrolytic copper and electrolytic nickel, you see especially for chloride and nitrogen, higher readings, what means at the end, very likely these are co-deposits from the electrolytic copper process, and the electrolytic copper bulk analysis shows that these elements are quite low in concentration. So you already see here nucleation interfaces are prone to higher adsorption of plating additives, and by these two methods, by STEM and DSIMS, you have a chance to analyze these element concentration and have an idea, okay, which process maybe lead to a weakness of this interface integrity between stacked microwires. Adsorption of additives at interfaces. This is in general a very interesting and very important topic whenever you are in this metallization business. It is always the question how the process starts to nucleate on surfaces. Here, I will want to start with an example we have found by improvements of our electroless copper process. What we found is in general that rough surfaces are more prone to adsorb plating additives, and this is of course something we should avoid. That means as more rough a target pad of the microwire interfaces is, as more you will have adsorption of additives. So the first learning from this experiment was to keep the target pad roughness low. Roughness can help to clean a surface. So roughening the surface, clean a surface, and a rough surface gives for sure a better mechanical bond. But on the other hand, it is always a trade-off then with more adsorption of additives on such rough surfaces. So the target pad roughness should be not too high. But the electroless copper process in this example is also now very important to optimize in this regard. We can nowadays use electroless copper deposits which are leveling target pad roughnesses better so that we can prevent nodulation. And if this is as a precondition ensured, it will be also less likely that we have a strong adsorption of electroplating additives. So this was an interesting finding as a prerequisite prior to electrolytic copper plating to avoid any roughness or nodulation in the processes before electroplating, so that we do not have too many active growth sites later for adsorption of additives. The plating process now itself, you already know, we are using several different organic compounds here, leveler, brightener, carrier, and additionally we also need chloride as a complexing agent in these electroplating processes. And here you find a short introduction how the adsorption takes place when nucleation starts on the interface of stacked microwires. First of all, you see here an image on top, how the copper crystal nucleation will start without any plating additives. You will create quite uncontrolled rough copper plating. Therefore, usually the leveler is required to control the crystal shape, to have a uniform nucleation and crystallization. And by the leveler, you will create then very uniform shaped and, in this example, very small crystals. The leveler itself is attracted by the electrical field on the surface, and this let him adsorb on the surface, but normally the leveler will not get co-deposited into the bulk of the copper plating process. It will always grow with the surface and will stay adsorbed on surfaces. The next will be the brightener, which usually accelerates the copper deposition, what will lead to very rough copper plating if you use a brightening compound alone as an organic additive. Only in combination with a leveling compound, you will get the desired crystal structure and smoothness. You will get larger crystals with an increased ductility, but still crystals which are uniform and polygonal shaped to prevent any roughness. And this is then also the mechanical best structure of electroplated copper deposits. This we only show you to give you a better understanding that these additives for sure adsorb on interfaces, especially during nucleation of the electrolytic copper plating process. They are required to achieve the copper quality for best ductility and very good tensile strength. On the other hand, for sure, we should take care that they are not built into the copper deposit and that they do not remain on the interface by too strong adsorption. For those of you who like also to get a more visual idea what is happening during nucleation of electrolytic copper processes on interfaces, you see here a copper surface covered with chloride, which is, as I said, the complexing agent for the organic additives. Chloride usually create at the beginning of the process copper chloride complexes at the printed circuit board surface and at the interfaces of microwires. And then you have the adsorption of brightener and leveler, so the accelerator and inhibitor. And this is one theoretical idea how it might look at the beginning of plating. And now you can imagine, if you look at these structures here, the interface cleanliness might be here something you really have to care for. Here I have an example for you about two different scenarios you can run into. The first scenario is on top visible. You see here a build-up of electrolytic copper and a build-up of electrolytic nickel on top. And in between, you see that the crystallization from electrolytic copper, that this crystal grows in shape and in size, will be continued in the electrolytic nickel application. So what you can see on this green highlighted image, what you can see here is a so-called epitaxial grow of electrolytic nickel on electrolytic copper. What does it indicate now? If you see that this crystallization from one metal layer to the next metal layer will get continued, then you can expect a very good bond between the two metal deposits. So epitaxial growth of metal structures indicate a very clean interface. Nothing disturbed the continuation of the metal grow in the next layer. And by purpose, we show you here copper and nickel plating to show you that even different metals can have a very good bond by epitaxial growth. Of course, here we talk about metals which have the same atomic lattice and metals which have a similar atomic diameter. Only then you can expect this epitaxial grow. But this would be the same for copper on copper, of course. Here we have the same metals. And if you see this epitaxial grow between both layers, you can expect that the interface was really clean and no strong adsorption of any kind of chemicals have disturbed the growth of the next metal layer on this interface. At the bottom of the page, with a red highlighted image, you can see now the opposite situation. We have here a different electrolysis copper process. On top of this electrolysis copper surface, we have a lot of adsorbed additives remaining from the copper plating process. So the interface, which is indicated by the red arrow, the interface is highly contaminated, especially with chloride and nitrogen, which are clear indicators for electrolytic copper additives, which are remaining here. And the electrolytic nickel process will not start with epitaxial grow the nucleation. It will from the beginning nucleate with its own crystal structure, and here you can expect that adhesion will be not the best between both metal layers, even if you don't see any gaps, even if you don't see any impurities or dark spots which could you let assume that there's some dirt, even if you don't see it. If the epitaxial connection between both metal layers is not given, you have to expect a poor bond, and in thermal mechanical stress situations, these layers might separate later very easy. Here, to show you one more example about our studies, two electroplating copper processes in comparison. These are both processes from Atotech. So we have a process running with the so-called leveler A here. And you see the image for the leveler A on the top left side of this slide. And this is a typical image of the copper crystal structure of a very clean copper plating process. So this is an image of the bulk of this electroplated copper deposit. And analyzing by DESIMS now the purity of this copper deposit, you see we find for all elements which are of interest in this regard, we find very, very low concentrations of all these elements in this bulk of this electroplated copper deposit, where we have used the leveler A. At the bottom of the page, you see another example of another copper plating process using a different leveler type, leveler B. And here you already see that the crystal structure is not so regular. It is more disturbed. Okay, you see increased twinning in the crystals, what is not basically bad, but shows already you have more stress in this copper deposit. And at the grain boundaries, which are partially red circled here, you see impurities, deposits. These are segregations after annealing. So analyzing this copper deposit, you find then for all elements of interest, much higher readings. That means here you easily find 5 to 10 times more nitrogen and chloride and sulfur as an example. And this is then a clear indication. Here we have co-deposition of the additives, and this is triggered mainly by the used leveler. So the leveler finally is the main additive, which is also then triggering the co-deposition of chloride and sulfur, which are part of the brightener. So this only as an example of some of our studies we have done in this regard and our findings. Here now a summary for you. The main takeaways of this short introduction to stacked wire reliability is that starting with a target pad area, which needs to be, of course, clean, but should be not roughened too much, followed by electroless kappa processes, which are not tending to create nodulation on such target pads to keep the growth sites and the number of growth sites very low for the absorption of the additives. And of course, the electroplating kappa process itself. Here, you need the right combination of additives. Of course, it is not only selecting the right additives, you also need to find the right balance of the additives, that none of these additives is dominating the absorption on the target pad. And there are also other parameters you see in the following table, which also can be adjusted to avoid excessive absorption of organic additives on interfaces. And what we also found by our studies is that in general, systems with insoluble anodes have less absorption on interfaces. One reason is that the anode film, which partially continuously gets dissolved in the plating solution, this anode film increase the contamination of the electrolytic plating process over the time. And here we found a slight tendency, depending on the copper anode quality of the anodes. Here we found a slight tendency also that insoluble anode systems are much more stable over months and years in this regard, not creating this dissolving anode film in the electrolyte. Finally, as I said already, there are several parameters which are important. For sure, the right, it starts everything with selecting the right organic additives and to combine them in a way that they are balanced and no additive dominates during the absorption at the interface nucleation of electrolytic kappa processes. But of course, parameters like temperature, current density also are very important to adjust in this regard. So we found, for example, with high reverse pulse frequencies, that we can prevent additive absorption at the beginning of the plating process very much. That means at the end, in reverse pulse plating application, we found also a higher reliability of the stacked buildups. But also, the TOC of the electrolyte is of importance, as mentioned before, when we discuss the anode film dissolution in copper plating processes. It is, of course, of advantage to control the TOC and to avoid a strong increase of the TOC. For sure, plating additives degrade by themselves and also contribute to the increase of TOC. Here, most of the additives are already selected in a way that even the breakdown products do not harm the process in any way. However, leach out of dry film, drag in of other chemicals, and of course, the purity of raw materials like copper oxide, like sulfuric acid, also have to be considered in this regard. So also these raw materials needs to be selected in a way that any kind of contamination can be avoided and absorption of organic chemicals will be prevented on interfaces. So these have been our findings so far in regard of the stacked microwire reliability and the dependency from the electrolytic kappa process. Finally, I would like to introduce you now briefly into our developments, which are based on this on these findings, starting with our vertical processes here. You see our latest kappa filling process for vertical systems. InPro MVF2. This is a process which works with insoluble anodes and copper oxide replenishment. Applicable in vertical conveyor lines, but also in vertical hoist lines. And this new development has a big advantage that you can also run the process with higher acid concentrations, around 100 milliliter per liter, what gives you the advantage to have an unmatched surface uniformity at the end, and also get a really good throw in through wires. In this way, you can combine copper filling and through wire plating with really excellent results due to the increased acid concentration we can use with this process and still have a very good copper filling with a very low plating thickness on the board surface. This combination is really impressive and gives you many advantages at once. For vertical through-hole filling and in combination with micro wire filling, you see here the latest process InPro THF2. Only to show you the improvement itself from the standard process to this new generation of through-hole filling, you can see here at really practical current densities of 2.8 ASD, we get with a new process, THF2, a very good microwire copper filling, and we can mostly prevent inclusion in microwire or in through holes. Even in through holes which are very narrow and not perfectly drilled, we get much better inclusion-free results. This is a nice combination. Finally, for IC substrate, what is a pattern plating application in general, we have here our InPro SAP3 process, give you at really good high current densities of 3 or 4 ASD. It gives you a very good surface uniformity in pattern plating application. And on the other hand, a very nice line shape, which is nowadays also very important to control in the IC substrate application. For horizontal processes, we have meanwhile developed a pre-plating process for flash plating or especially for MSAP application here. This new horizontal flash plating or strike plating process is excellent even for microwires which are maybe not perfectly drilled and where we have glass fiber protrusion and other irregularities at the hole walls. We can level with this new developed horizontal flash plating process the microwires very well, that we have a good precondition for later copper filling, that the copper filling will be inclusion free and also undisturbed during nucleation. After flash plating, you need the copper filling, and also here we have for horizontal and very well established, but meanwhile improved process called Impulse 2HF9. And this process gives you an unmatched copper filling, what means you can fill really large and deep microwires with a very, very low plating thickness on the panel surface. So this process is one of the standards for any layer and helic application in the industry. And also in the horizontal application, we have a through-hole filling process here based on reverse pulse plating. And this process, you see here examples, is of high interest nowadays for the thermal management of printed circuit boards, inclusion-free copper filling of through holes from 50 micrometer to 500 micrometer, and panel thicknesses of 0.5 of 50 micrometer up to 1 millimeter. These copper filling applications we are focusing on with this process. This is, as I said, very interesting for the thermal management of advanced printed circuit boards. So these have been the processes which are developed based on the knowledge we have collected in the past years to improve the stack microwire reliability and to reduce the absorption of plating additives in the copper deposits. I hope this was of interest for you. And now feel free to listen to the questions, and yeah, I hope we have some good answers for you. Thank you.
Okay, thank you, Roland. It was a pleasure to see and to hear your presentation. It is time to proceed with our Q&A session, indeed. I would like to remind you that we will cover as many questions as possible during our Q&A session, and all the rest will be answered by Roland after the webinar via email. So we've received many questions. Let's start with the first one. Have you also carried out studies with eco-packed polymer or other similar direct metallization alternatives to E-less copper?
So far, we are also running tests in our laboratories with direct plating processes. That's right. At the moment, we are focusing very much on MSAP application. That means here we are working with our flash plating application on such surfaces. And as mentioned before, here we found that target pad roughness plays a very important role. That the target pad has to be clean is logical, I think, to get best adhesion and a very good reliability of the interface integrity. But here we also need to avoid a very strong roughness. So when you have to clean target pads from any kind of residues from direct plating processes like carbon or graphite, then in this case, maybe you need to consider to keep the roughening effect of the cleaning very low. For EcoPact, we do not have this problem. Keeping the copper surfaces always free from the polymer. There's no etching required, at least no strong etching. And so the precondition of the target pad after EcoPack is very good to have a very low additive absorption at the end. And so we have a very good integrity.
Thank you, Roland. The next question is, can you tell something more about influence of aging of copper bath and E-less type with regards to reliability?
Yes, so there have been several studies about the co-deposition of additives, plating additives, by increasing TOC. These studies have been also published by several institutes. In general, you can say if the TOC increase is created, if the TOC increase is caused by the plating additives themselves, you do not have to expect more adsorption of plating additives, because the breakdown of plating additives usually do not contribute to an increased adsorption of additives in the plated copper deposit. If you have the TOC increased by any foreign chemicals, as mentioned before, for example, you have strong nitrate contamination in the copper oxide powder, what is a common problem. If you have, for example, other organics in the sulfuric acid, which is not very clean, and so on, these organic chemicals also containing nitrogen, also containing sometimes chloride or sulfur. And if you drag in such elements or the leach out from dry film, for example, the dye of the dry film, all these elements contributing then to the adsorption of chemicals on interfaces. And here we see a strong impact. That means leach out of dry film for IC substrate application. This is something you have to control very much, that you have not additional contributors to this organic load on the interface. For the electroless copper type, we have clearly seen a difference, and as mentioned in this short introduction, it depends how good the electroless copper can level the target pad roughness, or on the other hand, it depends on the nodulation of the electroless copper. If you can prevent this nodulation and have a good leveled electroless copper deposition, then absorption of plating additives is also very low.
Okay, thank you, Roland. Now we had a combination of questions. So let me start. Is high reversed current at the beginning better to prevent organic contamination? And what about the E-less copper layer? And will it be easily etched with high reversed current density?
Yes, so let's start with okay. This
Let's
is
start with the
special.
first part.
Yeah,
Yeah.
no, this is no. This is a special question here. We talk about reverse pulse plating in both cases. So in general, when you apply a very strong reverse energy, of course, there's always a risk that you damage electroless copper layer, which is quite thin, especially inside the microwire. So that's clear. If the reverse charge is very high at the beginning of the plating process, then the electroless copper deposit might get damaged, and then you have voids. When you apply now a very strong reverse pulse, on the other hand, you clean the surface by this reverse pulse. And cleaning means also during nucleation of the plating process, you have adsorption of additives and clean them. You etch them away, and so yes, you can reduce the adsorption of plating additives by stronger reverse pulses, by stronger reverse charges, but the risk of course will increase to damage the electroless copper layer.
Okay. Thank you. So the next question is why are nanovoids visible on page 5, and what is the reason for nanovoids at the interface?
So
I think it was
yes,
this one, if I'm
this one.
correct.
This is only an example image. Nanovoids can originate from different processes. So nanovoids can origin from electroless copper deposition. For example, if you have a lot of hydrogen evolution at the target pad, it might be that some of this hydrogen in its adsorbed condition will stay there and get co-deposited and incorporated in the electroless copper deposit. And later, during a thermal stress application, this hydrogen can accumulate to smaller gas pores, and then then it gets visible. So it can be encapsulated hydrogen from electroless copper deposition, but it is also known that electroplated copper creates such micro or nano voiding because of stress inside tensile stress inside the copper deposit. So you know that as more irregularities you have in the atomic lattice of copper, as more vacancies you have, as more sliding planes or twins you have, as more the material, the copper will create later at grain boundaries very small voidings. And this can be also one reason to see at the end nano voiding. And there are many more reasons, but these are two general reasons why you can run into this nano voiding problem.
Okay, thank you. So let's continue with the next question. Is pretreatment prior to ECD copper important for the interface reliability? What has to be considered?
Yes, we did not cover this today, but we saw it is a part of our troubleshooting approach in general. If you look at the fishbone we have discussed today, you will see that there are several very important things to consider when you do pre-treatment of your boards. And on one hand, it is always important to have a very good wetting of the microwire and the target pad. Of course, you also maybe want to remove some dirt remaining from other processes in this area. For example, even electroless copper deposits sometimes are not perfectly rinsed inside the microwire, and then you want to remove alkaline residues from the electroless copper process. And all this, therefore, is a pre-treatment very helpful, but you have to be careful when you use any kind of cleaning chemistry. It is for cleaning chemicals very easy to get into the holes because the wetting capabilities of cleaner is often very, very good nowadays. But on the other hand, you also have to rinse thereafter the holes very, very nicely and very good. If you if there's some cleaner remaining in the microwire and on the target pad, this is then, of course, again, a starting point for adsorption and increased contamination of this interface. So pre-treatment is very important, but rinsing is also a very important part of this.
Okay, thank you. So the next question is, testing PCB stacks under the reflow conditions several times stresses the buildup mechanically tremendously. What are the needs to be considered?
I think I did not got the question well. Can
So,
you maybe repeat? Mhm.
the question is a combination of a statement and the question. So
Yeah.
first, the statement. Testing PCB stacks under reflow conditions several times stress the buildup mechanically,
Mhm.
and it is tremendous effect. What are the needs to be considered?
I still have a hard time to understand exactly what the question is.
Let me
Uh,
publish the
sorry.
description.
Yeah, maybe you can publish this and then I can read it through. I'm sorry for this. This is.
Yeah,
Uh-huh. So where is it? One moment, please,
it's in
because I.
Q&A published.
Yes, published. Ah, here. Okay. So, okay. On one hand, I understand the question, but there's a lot to discuss in this case. Starting, of course, with the selection of the materials itself. So, whenever you want to prevent uncontrolled expansion of the thermal mechanical stress boards, you have to find materials which, in general, do not expand too much, where the CTA is low. Um, on the other hand, you also have to avoid any um, liquid adsorption inside microwires and inside the build-up that later this might slowly evaporate out of this build-up. So for me, as far I understand the question, there are many, many um, things to take care for. And sorry, I cannot answer it in a simple way. Sorry.
Okay, thank you. I think the viewer can reach you via email if he needs additional
Mhm.
explanation.
Mhm.
The next question is, you stressed the importance of leveler type during the presentation. Is this the main field of additive studies for reliability or not?
No, it is as you have seen. We look at all parameters of the plating process, and we found that the current density, the temperature, and so on are also very important parameter you can adjust and you can modify in production. At least you have some possibilities to optimize here, and often these parameters already give you a strong improvement already. So the leveler itself is for sure the main additive causing adsorption of organics on interfaces. On the other hand, it also depends on the brightener, how much a brightener can work against this absorption of leveler chemistry. That means here we have a competitive situation between additives. And when you change a leveler, it is also possible not it is also possible then to change also the brightener and to take a look if this combination at the end also works well together. So in my example of leveler A and leveler B, the chemical setup of the processes have been the same, except the leveler was exchanged against the other one. But if you continue your testing and also consider different brightener chemicals, then for sure you will also maybe get a good result with a leveler B type.
Okay, thank you. So the next question is, are hybrid suppressors better in regard of interface reliability than pure leveler?
So nowadays, most of the leveler used in printed circuit board application and semiconductor application are hybrids. So that means we did not consider to use the older generation dies in some of our processes. Dies have a big advantage for very good leveling and throwing power in high build-ups of multi-layer boards. On the other hand, it also depends on the die itself, but to have better control about plating thickness, uniformity, hybrid levelers are more common. But it is hard to say it is better or not in regard of absorption. This also depends on the die type you are using. So finally, it is more common to use hybrid levelers nowadays. It is the standard because of many technical reasons. On the other hand, a die might be still an option if you find a good one.
Okay, thank you. So now we have another bit of a complex question. Stacked blind microwires should be a copper-to-copper interface. But in this presentation, we saw a copper-nickel interface study on contaminations like carbon, oxygen, and chloride. Why don't we use copper-to-copper to study? Or does only copper-nickel interface can show the contamination between interface?
Good question. So one reason we study mostly copper on copper adhesion in our company. That means it was an exception that we also done some of the testing with copper nickel. So you are right. What I've shown you today is not the usual situation you face in production, and of course is maybe a little bit confusing if you look at this. First of all, we cannot show you many of our copper to copper studies because these are all in cooperation with customers of us, and these images are confidential, and so we cannot show them. And that was one reason to choose then another example, which is also more impressive in my opinion, because to see that copper and nickel can have a perfect epitaxy if the interface is clean should convince you that this is even more likely than for kappa-kappa adhesion, for kappa-kappa build-up. So I'm sorry that I was not able and it was not allowed for me to show you real production samples from stacked microwire build-ups during this webinar. But at the end, I thought this kind of imaging and example is also impressive. But you will find the same interface problems. You will find the same element analysis between kappa and kappa deposits. So there is no difference. This is at least what I can promise here.
Okay, thank you a lot, Roland. This will be the end of our Q&A session. And in general, it's time to wrap up our webinar session. Thank you, everyone. We really appreciate you being here. Soon you will receive the replay link for this webinar. If you like this session, feel free to share the webinar link, which you will be able to view after the receiver registers. For our upcoming and on-demand webinars, please visit autotech.com/media/webinars. We will also keep you updated about our webinar schedule via email. Stay healthy and safe. See you next time. Thank you.